Astronomy, the study of celestial objects like stars, comets, and galaxies, is one of the oldest disciplines of science. From time immemorial, early civilizations of the Babylonians, the Greeks, and the Indians are known to have made methodical observations of the sun and the night sky. And based on what they could see with their naked eyes, they speculated and theorized on the nature of the universe. Then, around 400 years ago, Galileo Galilei invented the telescope in Italy. This invention spurred astronomy to develop into an exacting discipline and revolutionized our perception of the universe and Earth's place in it. Yet, when we look at the sky, it seems to be serene and unchanging because we can see very little of what is taking place in the cosmos, even with a telescope. Astronomers perceived the universe to be fixed and tranquil until the arrival of a 19-year-old Subramanian Chandrasekhar at Cambridge in 1930. It is to him, a couple of decades later, that we can credit the uncovering of the true nature of our universe. Explosive, energetic, dynamic, ever-changing.
India has had a long tradition of scientific inquiry. Legendary physicians, mathematicians, logicians, physicists, metallurgists, and alchemists. Aryabhatta, born 476 Common Era, was one of the first in a line of great mathematician astronomers born in this country. His major work, Aryabhatiya, is a compendium of hypotheses which have proved extremely accurate. For example, he pointed out that the Earth spins on its own axis, that the Moon moves around it, and that they rotate around the Sun. He had explanations for day and night, lunar eclipse, and solar eclipse too, and had even calculated the length of a year to be precisely 365 days. His works were translated extensively into Arabic and Greek a couple of centuries later. And it is this grand tradition of Indian scholarship that Subramaniam Chandrasekhar carried forward, unraveling the music of the spheres backed by the power of elegant mathematics.
Subramaniam Chandrasekhar was an outstanding scientist of the 20th century.
Of course, his book on black holes was probably the greatest intellectual achievement.
I must say, Chandrasekhar was my role model, my idol.
Chandrasekhar was born at Lahore when India was still a colony of the British Empire. And science education on the whole left a lot to be desired. From childhood, Chandra showed a remarkable affinity for mathematics. But his father, C. Subramaniam Iyer, Deputy Auditor General, Railways, pushed him to pursue physics instead. Influenced maybe by his own younger brother, Sir C.V. Raman's success in the field, and also for better prospects of getting a government job. Initially, the Iyer family children, Chandra, his younger brother Balakrishna, and sisters, were taught at home in Mylapore. Later, he joined the best school in Madras, the Hindu High School at Triplicane. Decades later, he visited the school with his wife Lalita, a couple of years after receiving the Nobel Prize. She was delighted to find his records stand testimony to his brilliance in mathematics even in those early years. and being declared eligible to pursue further studies. In the beginning, Chandra found formal education not very motivating. Only when he discovered that the curriculum included algebra and geometry did he get really excited. Every year, he would complete the science and mathematics syllabus during the summer vacation itself, even before the school reopened. Teachers were in awe of him and regarded him a prodigy.
While at school, Chandra received a prize, the famous textbook, The Internal Constitution of the Stars, by the distinguished British astronomer Arthur Eddington. This was Chandra's first introduction to astrophysics. In 1925, Chandra enrolled at the Presidency College, Madras. Here, he studied physics, chemistry, and mathematics, but also seems to have had an innate enthusiasm for English literature. Chandra found himself drawn to physics rather than chemistry. Inspired by Srinivas Ramanujan, he wanted to specialize in higher mathematics, but had to enroll in the physics honors class in deference to his father's wishes, which he later acknowledged as having benefited him immensely. When the famous German physicist Arnold Sommerfeld visited the college, Chandra learnt from him about the discoveries of Fermi and Dirac, of the new quantum statistics and its application to electron gas in metals by Sommerfeld himself. Inspired, young Chandra looked for a problem where he could apply the new statistics. After only a couple of months of research, Chandra arrived at an interesting result that he described in a paper entitled The Compton Scattering and the New Statistics. He sent this manuscript to Ralph Fowler in Cambridge, whose work he was familiar with. And soon, like his illustrious uncle C.V. Raman, Chandra had his paper published in the prestigious proceedings of the Royal Society of London, while still an undergraduate student.
And Fowler connection started. And the following year, when even before he completed his graduate degree, he was awarded the Government of India scholarship to go abroad. And then obviously Fowler became his thesis advisor. In some sense, it bound him to astrophysics. It bound him to Fowler.
Chandra is best known for his celebrated discovery of the Chandrasekhar limit, derived during his voyage on a steamship to England. Chandra was interested in the final states of collapsed stars as determined by electron degeneracy. He had already studied the works of Arthur Eddington and Ralph Fowler before beginning his calculations. Chandra's crucial insight into this problem was to realize the importance of relativistic effects. Once relativity was included, he was led to an astonishing result, that a star more massive than a certain limit could not exist as a white dwarf at all.
Chandrasekhar made several important contributions to astrophysics and applied mathematics. One of his major contributions is identified with white dwarf stars and is known as the Chandrasekhar limit. It tells us that a star cannot retain its equilibrium as a white dwarf unless its mass is less than a certain limiting mass, which is approximately 1.44 times the solar mass.
When Chandrasekhar arrived in Cambridge in the 1930s, the university was, of course, one of the real hotbeds of science. R.H. Fowler was here, and of course he was the official advisor for Chandra, and so he was in probably the best possible environment. Of course, the groundwork for quantum mechanics had already been done by Schrödinger, Heisenberg, etc., and by Dirac, and so Chandra was at the optimum age, really, because he absorbed these ideas when he was young.
The early part of the 20th century were exciting years in the history of Western science. A series of extraordinary theoretical breakthroughs had ushered in quantum mechanics and thrust a new modern scientific era upon the world. Cambridge was the mecca for scientists, a time of great vitality and confusion, a time of transition from classical to quantum physics, and young Chandra had his sights firmly focused on the distant firmament.
Chandra attended lectures by Dirac, Fowler, Littlewood, and other luminaries. With so many famous names and an array of fascinating subjects: operational calculus, functional theory, generalized dynamics, statistical mechanics, Chandra was almost dizzy with excitement. The next 5 years were perhaps the most brilliant phase of Chandra's long and illustrious career. He obtained several fundamental results which are now recognized to be at the base of modern astrophysics.
The discovery of pulsars, burst of neutrinos from supernovas, and the fact that the measured masses of neutron stars are almost equal to 1.44 solar masses are spectacular confirmations of the predictions made by young Chandra in the 1930s.
After pursuing quantum mechanics for a year in Europe, Chandra returned to Trinity College, where he obtained his doctoral degree in astrophysics from Cambridge University. Soon, to his utter surprise and delight, he was elected to the Prize Fellowship at Trinity College under the stewardship of J.J. Thomson. But the end of his 3-year scholarship was soured by a difference of opinion with Arthur Eddington at a meeting of the Royal Astronomical Society here at Burlington House in London. This controversy was to influence the way Chandra worked for the rest of his career.
At the January 1935 meeting, Chandra postulated his theory of the limiting mass of white dwarf star. It confirmed his earlier results obtained on that voyage to England by more rigorous and complete calculations. But no sooner had Chandra presented his paper than Eddington stood up and rejected the young man's results, not by any scientific argument, but by ridiculing the very combination of special relativity theory with quantum statistics. The whole episode was tantamount to a public humiliation for Chandra.
I think that was Chandrasekhar's great contribution, relativistic degeneracy, which he introduced into astrophysics. And Eddington just could not bring himself round to accepting that idea. It turned out Chandrasekhar was right and Eddington was wrong.
Eddington went on attacking him, but Chandra did not do anything. So why did you do that? And then Chandra made the famous statement I quote. I saw, I was young and I was 30 years of research, and there was no reason harping on the same string. It has happened, forget it and go on. He made that decision, and that writing that book and working on another book, he got into this new pattern of his, work on a particular area for a certain length of time, write a number of papers, and write a monograph and go on to another field and so on. He became inward bound and not worry about whether it is recognized or not.
The era of relativistic physics began with Albert Einstein, who realized that space-time is not a stationary stage on which events play out, as Isaac Newton had envisioned. Instead, space-time can bend, twist, and warp, very much like a trampoline reacting to a child jumping. Early on, Einstein realized that Newtonian mechanics was insufficient to reconcile the laws of classical mechanics with the laws of the electromagnetic field. This motivated him to develop his theory of relativity. 2 years later, Einstein applied this theory to model the structure of the entire universe, which still holds good to this day.
The cosmological constant.
At the International Astronomical Union, Chandra noted that Newton not only postulated a universal law of gravitation, but also worked out all its consequences. The first equations describing planetary systems, satellites, and comets. Newton didn't just invent the law, he also believed deeply in his own theory. On the other hand, Einstein wrote down the fundamental field equations but did not work out all their consequences. Ironically, he did not realize three major consequences of his own theory: the Big Bang, black holes, and gravitational waves. As Chandra pointed out, we now know that he was wrong to have not believed more strongly in his own theory.
In 1937, after the Eddington controversy, Chandra decided to leave Cambridge. Back in Madras, he married Lalita Doreswamy, a co-student at the Presidency College, and soon they were on their way to start a new life in America. Chandra took up a research position at the Yerkes Observatory in Williams Bay, about 70 kilometers from the main campus of the Chicago University. Otto Struve, the then director, was in the process of hiring some of the most brilliant young astronomers and astrophysicists from around the world, and Chandra was one of them.
In 1897, the University of Chicago's Astronomy and Astrophysics program began with the construction of this observatory here in Wisconsin, thanks to a handsome endowment from Charles Yerkes, who had made his fortune with Chicago's electric railway. Interestingly, Yerkes Observatory prides itself as the birthplace of modern astrophysics. It is a fascinating example of the architecture and technological accomplishments of the late 19th century.